All right. So here we are. This is page 172 in the textbook. All right. So example number 8 says a lawnmower of mass 12 kilograms is being pushed by a force of 150 newtons horizontally and 40 newtons down. So this is kind of weird. This is a little different. We've got 150 newtons horizontally and 40 newtons down. So they've broken it into components. Alrighty, so as I was saying there before I was rudely interrupted, 150 newtons horizontally and 40 newtons down. If the kinetic coefficient of friction between the wheels is 0.9, between wheels and grass, 0.9? Are you kidding me? Find the force of friction acting on the lawnmower. Now you'll notice there is one thing that is not mentioned at all in the question. What do you think? Anything that you sort of think might be missing that might be valuable? Direction. You're kind of on the right track, but when you push lawnmowers, I don't know if any of you have pushed a lawnmower or not. Well, that's true, Martin, but they've actually broken into components already. So maybe let's draw the diagram first, and then we'll go from there. Okay, so we got 12 kilograms. Now it's 150 newtons horizontally. It's a push, but generally, remember, we draw free body diagrams sort of as if they're always pulls. So we're going to put our 150 there, and 40 newtons down. Okay, so like it's actually being pushed. Maybe I should draw it like this. I hope you guys are using pencils. Maybe we should draw it like this. Right? FA, right? So this would be the 150, and this would be the 40. Maybe that's a better way to show it. Right? And then we still have weight force, and we still have normal force. Now the 40 newtons, the horizontal, the y component of the applied force is going to affect that normal force, right? But the one thing that's missing is how fast is this thing moving? Is it at a constant speed? Like when you push a lawnmower, do you start at one side of the lawn and then accelerate to the other end of the lawn? I've never seen you do that, Pat. I'm setting you up there, Josh. Yes, yes. So anyways, most of you likely are pushing at a constant speed, right? But it turns out that if you actually look to example number 9, the next question actually says, what's the acceleration of the lawnmower? So it's kind of weirdly worded. Well, you could be, but I mean, at some point you're going to stop accelerating, right? It's not like you're a motorbike. I mean, even an engine, any kind of engine car is going to stop accelerating at some point. So here all you are to find is the force of friction acting on the lawnmower. So we're probably going to use, don't write this down, mu equals FF over Fn, right? Because I've got the mu value, I'm trying to find FF, so I really need to find the normal force, right? And generally the normal force and the weight force are equal to each other, but in this case they are not because we have this 40 newtons down. So you'll remember yesterday I showed you that the vertical component, the overall is 0. Remember how I showed you that? Okay, so let's just say, how about we write Fn let's do it this way. Sorry. I don't even know why I'm holding these notes in my hand because I'm not even looking at them. I'm going to write F net y is equal to Fay plus Fn plus Fw, and the F net y is equal to 0. Right? There is no acceleration up or down. So that's F net y is equal to Fay plus Fn plus Fw. And the Fay is that 40 newtons, and that is directed down, so we're going to make it negative. The Fn is what we're trying to solve for, and the Fw is, oh, we don't know yet, do we? And I've kind of, how can I fix this problem here where I haven't really found the Fw yet? Can I just put m times g in there? Okay, so we're going to put plus 12 times minus 9.8. Let's do it like that. So minus 40 plus Fn, and that's going to be 12 times 9.8, which is 100 and what? 198? 198.4, Sean? 0.6? I didn't grab a calculator. Okay, so that makes, hey? I don't even have a calculator. I'm just listening to numbers that are coming out of. Sean's mumbling? Okay. So the 40 and the 117.6 go to the other side, and you're going to be left with, well, how about we round it up and we'll say 158 newtons. And now we can put it over here. I'm going to do it down here. So that's going to be a whopping 0.9 for our frictional coefficient. Friction force, the normal force is 158, giving us a friction force of 142. (142 newtons of friction). Now, how much is the horizontal applied force? 150. So is this lawnmower going to actually move? It should, right? The applied force, the 150, is greater than the 142. And in fact, that's what they're asking you to do in example number 9, is to find the actual acceleration. Right? So to do that first, we're going to have to find the F net x, the overall sum of x forces. So that would be FAX plus FF. 150. Now the friction force, you have to manually make it negative. What was it? 142. So you get an F net of 8. And this lawnmower ain't going very fast. I guess it's that. So 8 divided by 12. 0.7 meters per second squared. So apparently the lawnmower is continuing to accelerate as the kid pushes the lawnmower across the lawn, because they lost a bet against the guy who bet against the Heat versus the Cavaliers. No, Spurs, right? Do you want to try number 10 on your own? Is this what your free body diagram looks like? Now you got to be careful here, because it says one person is pushing from the right, which means it's to the left at 50, right? And the other one is to the left with the force of 80, so to the right. So what's the first step? You got to find the. Can I write it as F net x? Does that make sense to you? Right? And the solutions, I'm starting to sort of use this terminology. The solutions aren't going to sort of reflect that, and I'm not likely going to go back and fix them. But I'll write F1 plus F2, so that would be like, I guess I got that backwards, right? So I'll have to go minus 50 plus 80, so that's going to be plus 30, right?
Interruption, could we have Mr. Klein or...
And so that's our applied force. Oh, now there's friction as well, right? So I guess technically my free body diagram should have that on there, right? And how do I know it's to the left? Because it's on the right, yeah, exactly. The greater force is on the right. So now let's find the weight force. Mass times gravity. 50 times minus 9.8. 490, right? Yeah. 490. And now mu e, oh, I guess I really should say, therefore the normal force, that's negative, so the normal force is positive 490. So mu equals FF over Fn. 0.3. The friction force is what we're solving for. Normal force 490, giving us a friction force of 147. Actually, now you should really say that that is negative, because it would be to the left. And now what? Now, I guess this isn't actually correct here, is it? Because the F net X is F1 plus F2 plus the friction force, isn't it? Right? So really, I should have plus FF, and so this should be minus 147. So does that change this? Does that make this 30 minus 117? Say it again, Connor. No, I think you're on the right track. I want you to. What do you mean? Okay. I think what Connor's trying to say is that this 80 and the 50 give you an applied force of 30, but the friction force is 147. It's not going to move. Right? The net force, in fact, is going to be 0. Right? You're going to have to manually set it to 0. Why? Because the friction can't be more than the applied force. Right? Like if I just push on my desk here, which is firmly, attached to the floor, it's not like it pushes me back, right? Or it's not like it goes backwards, right? Friction only works as hard as it needs to, right? So if you only have a net applied force of that 30, friction is only going to be 30, right? It's not going to use it all. So in fact here, if the F net X is 0, therefore the acceleration also 0, because friction is greater than the net X applied force. A little different. Oh yeah, this one here. I'm gonna let you try this one for a minute or two as well. This one's a little tricky. Give it a thought. It's certainly a little different. So we got a 0.5 kilogram block that's being slid up a chalkboard with an applied force of 6 newtons upward and 2 newtons inward towards the board. The coefficient of kinetic friction is 0.4. Find the acceleration of the block. So let's draw this picture. I'm going to draw the chalkboard in this case, just to give a visual sense of what's going on. So there's this block, and it's going up, but don't draw an arrow going up because we're only drawing forces here, right? So it's got 6 newtons upward. So we'll call that, what should we call that? Label it. We'll call that F. Should we call that one just F1 maybe? Call that one F1, sure. And 2 newtons inward. F2. Well, that's 2. This one is 6. The coefficient of friction is 0.4. Calculate the acceleration of the block. Well, there's other forces acting here, right? There's also gravity. And there's also a normal force. But which way is the normal force? Straight up. To the left, says Connor.
Down.
Down, says Josh. We've got 3 directions covered. Well, of the 3, Larry, Mo, and Curly, Connor is correct. You're right, Connor. The normal force is always perpendicular to the surface, right? If this was flat, if I take, okay, I'm going to do this. If I take the whole thing and go like this, right? Oh, okay, that was a really bad idea. That was a bad idea, right? If the whole thing were like this, there's the weight force, there's the normal force. The normal force is perpendicular to the surface, right? So because the surface is vertical now, this is the normal force here. So the big question is, how much is that normal force? Well, I'll tell you what, it's the same as this one. Why is it the same as that? Well, because there's no acceleration left to right, is there? Right? So in this case here, the normal force is equal to 2.
Would it be negative?
Well, for now, let's just say it's left. Yeah, I understand what you're asking, but let's just keep in mind that it's left. We know it's left without making it negative. Can I find the wake force? I can. That's going to be mass times gravity. So 0.5 times, and there I slipped in a negative minus 9.8 minus 4.9. That's down, right? What's the up force? The up force is 6. But we're missing one more force here as well. Which one is missing? Friction. Okay, Josh, chance to redeem yourself. Which way is the friction?
Down.
Correct. The friction is down. How come?
That's because it's the force is being applied.
Because it's moving up, right? The motion is up. So in this case here, mu equals FF over Fn. The mu value is 0.4. We're solving for friction. That normal force now is that 2. That's the hard part there, right, Mark? That's what was getting you stumbling?
Yeah.
Probably?
I didn't realize the diagram was.
Yeah. It's a challenging question. And that's why it's an example, right? 0.8. Okay, so now it means that my net y, I'm going to write F net y is going to be equal to this F1 plus my Fw plus my FF, I guess, isn't it? So the F net y is going to equal the 6 newtons up. Let's make it positive. The Fw is minus 4.9, and the friction force would actually be minus 0.8, minus because it's down. So do we actually get a net force here? 6 minus 4.9 is 1.1, so it's 0.3, I think. Am I right? Yep. Which will give us an acceleration. 0.5a. Acceleration then is 0.6 meters per second squared. And just for clarity's sake, I better write up. Yes, a little different one than you've seen before. All right, shall we continue with this process here? You want to try number 12 on your own? You guys give number 12. This one isn't particularly weird. I guess I've been recording for the last 2 or 3 minutes, just sitting here doing nothing, so hopefully people go. I'm not doing that. The puck is moving along essentially frictionless patch of ice at 6 meters per second, and then encounters a rough patch of ice with a coefficient of friction of 0.1. So it's going along, and then when it gets to here the mu value is 0.1. Here the mu value is 0, right? Okay, so this is another one of those problems where there's sort of like 2 stages, 2 things happening, kind of like the car passing the truck, or I can't remember which way it was, but you know, on the test, right? So you got to stop, and there's the sort of 2 segments to the situation. It's moving along here. Its VI here is 6. How fast is it going when it gets to here? Also 6. It's frictionless. It's staying here at 6. So the VI here is 6. We do not know how fast it's going when it gets to the end of it, but oh no, we do. How long will it take for the puck to stop, right? So we know that the VF is 0 there. So during interval A, we would say it's traveling at a constant, an average of 6 meters per second, constant 6 meters per second. And then here, it's going from 6 to 0, isn't it, right? So you have to recognize those 2 things. How long will it take for the puck to stop, and how far will it travel? So I think that how far includes, well, we don't have a time here at all, do we? So maybe this isn't, as I read it again, maybe this isn't one of those 2-stage ones. Maybe it's just this, isn't it? I think it's just this, isn't it? Would you agree with me? Yeah, I think so. I think I was completely wrong there. All right, so we've got weight force, normal force, and I guess we have friction, and that's it, right? Oh yeah, so I think this is all doable here. Fw is equal to mg, 0.3 times minus 9.8. 2.9. Mu equals FF over Fn. 0.1. We're solving for friction force. I guess I should say the normal force is equal to positive 2.9. So that's going to be 0.29, right? For friction. And that friction is actually the net force, isn't it? Right? It's the F net X, isn't it, right? F net X is equal to 0.29. So F net X is equal to MA. Writing's getting worse. The mass is 0.3. Solve for acceleration. I get 0.97 meters per second squared. Okay, so we want to know how long will it take it to stop. So now we're into kinematics here, aren't we, right? So something like VF squared. How long? I guess we want time. I guess we probably want to say VF equals VI plus AT. That would be 0. The VI is that 6. Now, is that 0.97 positive or negative? It's negative. How come? Because it's slowing down, stopping, right? And you're going to have to manually do that. So you get a time of 6.2 seconds. And then to find out how far it takes to stop, so that would be VIT plus 1/2 AT squared. So that'd be 6 times 6.2 plus 1/2 the acceleration of minus 0.97, and our time is 6.2 squared. And I get 19 meters. That's a good little practice question. Okay, time for me to stop talking. There's some good textbook questions on page 188. They are numbers 39 to 48. There should be, I can put the solutions on Schoology, but there should be a link to all the solutions on Schoology anyways. Answers are in the back of the textbook. And I also, at the start of the period, I handed out the pre-test hand-in question. So if you want to skip right to that to see if you're ready for it, you can do that. We're going to start a lab on Monday. So I'd like that pre-test done by like maybe Tuesday or Wednesday. Is next week a short week too? I think it is, isn't it?
Friday.
Yeah, I think Friday's a day off though, right?
Yeah.
Yeah.
Oh yeah, Friday is.
Okay. So we will do the lab on Friday. It'd be really nice if we could power through that and get started and get it done in one day. Possible?